Okay, we're going to continue with what we started before with photoelectric effect and with Planck and Einstein's theories. And basically what happened is, up to this point, a lot of evidence has been coming out saying that light and EMR are particles. So if light has particle nature and acts as a particle, then what Compton explained then said, well, if a particle has energy, which it does, we say it has E equals hf, so then that thing must have momentum as well. So Compton said, well, how can we calculate the momentum of these particles? So if it's a bundle of light, a photon, it should have some momentum. The tough part is proving it, because we don't feel the momentum of light. It's so small, it's going to have such a small amount, we're not going to be able to feel it like you would getting hit by a ball. So because light and energy has no mass, we can't use our old formula of P equals mv. So what Compton did was basically modify Planck's formula, and we came up with P equals h over wavelength, or if we were using frequency, it would be P equals h times frequency over c. So how he proved this was he started shooting high frequency X-rays. So he'd shine X-rays on graphite, and the idea or the common sense would be if this was a wave and it diffracted or refracted, then it would slow down as it goes through the graphite. So if a wave slows down, it should get compressed and it should have a smaller wavelength, kind of like this picture at the top shows. So that's what was expected, but when Compton actually did it, he found out that the X-rays scattered at a different angle, and he found that they actually got faster, so the wavelength increased. So it's kind of weird that what's happening is it's kind of opposite to what we'd expect. So what Compton predicted was we've got some conservation of momentum going on. So what he said is we have some sort of momentum of energy coming in, so I'll just leave it as momentum. So we have this X-ray coming in that has momentum. He says it's going to lose some of it as it goes through the graphite, and the momentum that it loses is going to get transferred to the electrons that get ejected from the metal. So if we look at this, we can calculate the momentum coming in as P equals h over lambda. We can calculate the scattered waves as h over lambda. And they're going to be different because it loses some of the energy. And then the momentum of the electron, though, we still have to use our old formula. We have to use P equals mv, because the electron has a mass, so we would use our old momentum formula. So Compton did this, and he actually calculated two dimensionals and all these different things, and he found out that it was basically a perfect 100% conservation momentum. Or if you remember back when we started in the first unit, momentum quite often wasn't conserved because due to extra losses of energy, of heat and things like that. But in this case, at this microscopic level, Compton found out that it worked almost perfectly. And this was sort of the main turning point to say, yeah, this whole particle theory actually has to be true. If our particles are acting as or if our light is acting as particles and have momentum and we're getting conservation of momentum, then that has to be true. So from this point on, this whole wave-particle duality theory sort of took over. One other quick calculation, or one other formula, Compton figured out that because we're always getting this light coming in, it's going to hit the metal, it's going to scatter off at a different angle, our electron's going to get shot off at a different angle. He said we can basically always figure out what this angle is going to be, kind of like a refraction type of topic. So we'd have this particle coming in, hits the metal, it's going to refract at an angle, and he said we can calculate that angle, or we can calculate the difference in the wavelength using h over mc times 1 minus the cos of the angle. Key thing to remember, that angle is always going to be the angle to the normal, not the angle between the total. So because of that, we can now solve all kinds of questions using what we learned in Unit 1, the conservation of momentum, but now using these other formulas. So the first thing we want to figure out is we have our particle coming in, so we want to figure out its momentum. So it's h over lambda. So it says we have an X-ray with a wavelength of 1.2. So we'd have our 6.63 to the negative 34. We divide that by 1.28 to the negative 12. So if we do that calculation, we get 5.18 to the negative 22. And that's momentum, so that's kilograms meters per second. Okay, so now what we want to do is we want to figure out the scattered momentum. So we don't know anything other than we know the angle is going to be 15 degrees. So we're going to have to go back and use our new formula. So our new wavelength will be h over mc times 1 minus cos of our angle. So we want to figure out what the new wavelength is. So we put in our 6.63, mass of the electron, I won't bother putting the exponents, and times speed of light, and we times that by 1 minus cosine of 15 degrees. So you got to be careful, this is calculating what the change in wavelength is. So if we plug all of that in, we get 4.27 to the negative 12. So what that means is then our incident wavelength was 1.28. It's gained 4.27, so we need to add that on there. So when we add that, we would get 5.55 times 10 to the negative 12 meters. So that's our scattered wavelength of our outcoming ray. So we have our 5.18 going in. Remember, this one's going to scatter at 15 degrees. So now we can calculate that momentum the same way. So we'd go h divided by our answer. So that gives us our 6.63. We're going to divide this by our 5.55. So if we do that on our calculator, we get a momentum of 1.19 to the negative 22. Okay, so then we also know that the electron then is going to go off at some sort of angle. So that's what the question's asking is, what is the velocity of that electron? So the first part, what is the wavelength of the scattered X-ray? We've got that here. So now the last part is we need to figure out the velocity of that electron. So let's kind of redraw this. So we have our incoming momentum was 5.18 to the negative 22. And we've got our angled one at 15 degrees, and it was 1.19 to the negative 22. And we know our electron is going to go off something like that. So just like we did in the first unit, now what we want to do is we have to break this into vectors. So we need to figure out our horizontal and vertical components of the scattered photon, and we know then that's going to be the horizontal and vertical of our electron, and those momentums have to combine to what we started with. So let's do that first. So we'd figure out our 1.19 times it by the sine of 15. And I think I've got my calculator in radians, which actually screws up this calculation. So I'm actually not going to continue, because when I did the cos 15 in this step, I was in radians, so this whole answer part here is going to be wrong. So you get the idea. I'm just going to leave it at this. So we get the idea that, just going to kind of go back to this diagram. Let's just assume these numbers were right, the first thing we'd want to do is figure out our x and y vectors of that one. Then we know the x of that one plus the x of the electron would have to be the same as what we started with. And then our two y's would have to be equal to each other to cancel out. And then all we'd have to do is figure out our hypotenuse and our angle, and that would give us our momentum of the electron. And then we could figure out, once we have momentum, we could calculate the velocity just simply by dividing by mass.